So this is talking about some research that's come out of the University of Bristol, and we recently formed a startup company to try and commercialise this. It's called SenseDriven. It's really trying to avoid harvesters. So, okay, great. So I'm going to talk about, this presentation has got two sections. One is really the new opportunities that are brought about by sensor-driven electronics, such as sensor-driven domains, avoiding static power, and being able to embed things so that you can never get back to them again for decades. And then I'll show you some basic building blocks that we use, sub-threshold voltage references, detectors, protection, and talk about the commercial status, what we've been doing there, what sort of application areas we've been focusing on. So what is a sensor-driven domain? Well, if we take our the way that computing is normally arranged, where we're sensing something, computing and communicating, then we could call that a battery-powered domain. It has a stable voltage supply that's always nice and constant, and there's continuous strain because there's a clocked activity, or there's something going on all the time. And the aims are to do a lot for a little, and we want to do these things that consume power as infrequently as possible, such as sampling and communicating. And the sensor-driven domain is a domain that you can imagine as wrapping around that, and there's no battery involved. Instead, it's powered from these horrible signals that come out of the sensors. They're 3 orders of magnitude less power than an energy harvester. And here the aim is to survive these signals. So you've got signals here going, hovering around a few hundreds of millivolts, then going up to 20 volts. And you might have weeks between these two spikes if it's a rare event that you're looking for. And you're just trying to do as much as you possibly can, and using this to schedule battery-powered activity when it's important, when it's needed. And this sensor-driven domain can act on the sensing, so precise sensing, or the computing, or the communication. And its aim is really to eliminate useless data in the Internet of Things and also unnecessary power usage. So that's the purpose. You can also think of this as modifying one of our layers of abstraction. So normally the layers of abstraction, certainly the high-level ones, can be made to be event-driven. But when an event-driven layer is not doing anything, there's still power consumption because the lower layers are still doing stuff like sleeping, sampling, and timing. And the lowest physical layer is not normally event-driven. And in our case, we're making this hardware layer event-driven, and event-driven means when it's not doing anything, it's completely off. There's no power consumption. And it also, therefore, has to operate from intermittent voltages because you're not connected to the battery. So this allows us to eliminate static power. So if you're doing a lot of, if you're doing intense computing, then you're sort of stuck either with static loss or dynamic loss as you try and pick the technology node or the supply voltage you want to use. And as you do less intense computing or even sleeping, you find, as you all know, that you need to choose perhaps a larger node or a higher supply voltage to maximize efficiency. But there's always this no-go area because of leakage. And so with this sensor-driven approach, it allows us to use a circuit that doesn't use battery power to power gate off things and avoid this leakage, and therefore we can go into this no-go area. And so now you can operate optimized circuits for computational efficiency only. So what does this Powergating circuit look like? So we start off with a sensing element, and there are plenty to choose from. These need to be sensing elements that generate a voltage, and they output something like this. And then we add to it some sort of sensor fusion that might combine signals, it might filter them, and then a power gating circuit. So that's something that turns this, that it has no power rail, and it's powered off this horrible signal, and it outputs a lovely, clean, sharp power gating signal that we're used to in digital electronics. It's very important that this is virtually non-invasive, because sensors, unlike harvesters, they produce so little power that if you go and take a few nanowatts out of them, you're clamping them and you've lost your signal and your energy. So we need to make sure that we're down at picoamps and that there's no clamping, and that then allows us to bring in a parallel path, and when the battery-powered domain wants to do something with this signal, then it can do so. So, for example, we can then power gate on amplification, active filters, computation, whatever you choose to do. So we've got this sort of zero power mode in our sensor that sits there operating. Now let's see what that does. So its job really is to leave the electronics in a zero power state between events, and only switch things on when an event occurs, and it must never miss an event. And that's quite important. That's where one of the benefits of this approach has come in, because if you think of conventional battery-powered periodic sampling, you're sort of stuck between either being very efficient and having big gaps between your samples, or making sure you never miss an event, but then you've created a power-hungry system. So this now, if we use this system here, it enables in many cases, in monitoring cases, it allows us to have decades of lifetime from a microcell, so something smaller than a watch battery. And that means you can permanently embed your system. You never have to get to it again. And you can use that either for permanent sensing or for permanent receiving, for example, for remote control. So let's think about the building blocks that we've used to implement this. So we use a few basic things here. We've got a sub-threshold voltage reference, which is the lowest power voltage reference we've found. We think it's about 3 orders of magnitude less power than what's out there. A decision-making trigger, again the lowest power one that's out there, and some buffers. And crucially, they're all powered by the input signal. There's no voltage rail here anywhere. And the way, if you string them together, you get a voltage detector. And the way that works is, as the input voltage increases, then this voltage reference switches on only when needed, when the comparator needs to make a decision. Once that decision has been made and the output voltage has snapped to the input voltage, then we turn this voltage reference off. And so over time, that is a very, very efficient system. It really just behaves like a transistor that is extremely snappy. So this is your gate, that's your drain, and ground is the source. Or it behaves like a Schmidt trigger with no power rail. So that's what this basic building block really does. And it has very low power consumption. How do we do that? Well, if you look at the IV characteristics, so this is input current versus input voltage, as we ramp up the volts, we go from picoamps input to nanoamps. This is the detection threshold. For this particular chip, it's 0.6 volts. And then we turn the comparator and that voltage reference off. As you saw, the voltage the red trace disappeared. And so we bring it down back to picoamps. And that means we have a non-invasive system. When the thing is triggered, it's not really harming your sensor signal. And then as the input voltage rises further towards 20 volts, we find things might start to come out of sub-threshold, and then we disconnect our circuits. And that means it stays low power and they survive. So where are we today commercially? So we've recently formed SenseDriven Limited to commercialize this. And we've patented some of these building blocks that I just showed you, in particular this voltage detector chip here. So this voltage detector chip has 1,000 times lower power consumption than the best competition out there, and it's the only input power detector that combines a low detection threshold and the high maximum voltage survivability. So we initiated a sampling program in February, and we've been sent people that have sort of logged on and requested devices. We've been sending them this thing here. It's got a little SOT23 packaged voltage detector in it, and we weren't quite sure what people might use it for, but devices have been requested by 70 commercial partners, and if you'd like a sample, please log on to SenseDriven.com. So what have people used this for? We were quite amazed at what people used it for. It wasn't necessarily what we'd had planned. So anything, wake parameters from temperature, motion, strain, all the way through down to chemical concentrations are being trialled. And what sort of industries have been asking for these devices? Well, I can't really say that there's one of these that is most dominant. Perhaps the consumer electronics is least dominant of all of these. We have had some requests from here, but there's some really very industrial applications here, a lot of asset management, so a lot of things that I'd never heard of before. So I feel I understand the Internet of Things a little bit. It's not tweeting toasters. There's actually some really important applications here. So because we're under NDA with a lot of these companies, but I still wanted to show you sort of what they're doing, I've put together this case study that sort of shows what they're doing, but it's not specific. So this is a case study comparing our technology to world-leading microprocessor solutions, i.e. very, very low power Texas Instruments timers combined with microcontrollers, just to really try and eke out maximum performance. So the first example is a size reduction example, and here we take traffic monitoring. This is a button that requires a five-year lifetime. It has to send out weekly text messages. It's on a motorway. There's a car going past every 5 seconds. It's 5 millisecond duration, and I've assumed quite a hot temperature, which means you've got more battery leakage than at room temperature. And so here we get a 51 times reduction in battery capacity needed. So you can power this functionality off a small watch battery for 5 years using SenseDriven. The other thing people are doing, and probably more people are doing this, is trying to extend lifetime to something that allows them to embed the product. And here there's an example set, a thermal label for over-temperature alerts. Here I've taken a very, very small battery, so this is smaller than a postage stamp. It's a thin film lithium manganese dioxide cell, doing one chirp per event, and there's 6 of these events per year, so these are events that people need to catch with a relatively quick response time. And here we get an 11 times increase in lifetime compared to the absolute sort of what we think is the world-leading polled solution. So just to summarize, as a company, we've got proven silicon and we're seeking commercialization partners. The sensor-driven devices that we've got, they listen for free, they don't miss events, they leave the signal intact for further use. They are configurable, so as you saw, there was a wide range of sensors and measurement parameters that are applicable to this. It's a very sensitive device. It has a configurable threshold. It protects you from the sensor voltages, and they're just really building blocks for new low-power circuits. It's quite amazing what you can do with these things. So we put together a temperature sensor that consumes so little current that if there was no internal leakage, self-discharge in your watch battery, it would last for 800 years. We put together boost converters, all sorts of things. So if you leave these in the lab, the guys just start making stuff with them. Essentially, it's an inverter. An inverter, as you know, is like a useful building block to build all sorts of things. But crucially, it doesn't require a power rail. They're very compact and cost-effective because you don't need the energy harvester. So our conclusion is that batteries are actually okay for embedded IoT. We can get decades of operation from them. Thank you.